So the paper we were discussing is flush bus read. Last time there was a lot of background, so we couldn't talk about the main contribution of the paper, our main idea of the paper. So let's go through it quickly. And if you have questions, you can ask, but then spare some questions for the discussion part also. Okay. But if you think like that, your questions are critical, you can still stop. Okay. Okay. So this is like uh, this is like the underlying architecture which is assumed by this one, where you have multi-core processor and last level cache LLC. It is shared among multiple cores, but L1 and L2 they are private. And here in this example, we have two cores A and B. And we assume that, let's say, victim process is running on the core B. So at the same time, definitely the code and the data which this process want to run is residing in memory. As last time we said that we need the page table because the addresses generated by any process, they are virtual addresses, but we cannot use the virtual addresses to access them in memory. We need physical addresses, therefore we need the translation, and that translation is done by using the page table. Every process has its own page table. So let's say this is page table B for the process B, and it has two, among other, it has two entries. Now let's say if let's say we are assuming 64-bit architecture, which means that virtual address space is from all zeros to 64 ones. So this virtual address is consisted of 64-bit. So when you want to convert it, when you want to use this virtual address and translate it into the physical address, what you do is that you break the virtual address into two parts. What is the width of each part? It depends upon what is the size of your page. So here we are assuming that the size of the page is 4 kilobytes. So if it is 4 kilobyte, then the number of bits you need to address any location within that 4 kilobyte is you need 12 bits. Okay. So we are subtracting 12 from 64. The remaining 52 bits, they are used to construct the page number. So this page number is then used to index the page table of that process. Let's say it points to the entry which has some content like this. So this is the frame number. So based on the page number, we look into the table and it gives us this physical frame number. Okay. And, and then that physical frame number itself, this number is 52-bit. Then this physical frame number is combined with the remaining 12 bits from this virtual address because they work as an offset within the table. I'm not going to explain how it works, but I just, for those, if you have already taken the OS course, you should be aware of how it works. If not, go and have a look at how virtual address is broken down into two components, which is offset and the page address. Okay. And what are the factors which affect it, the size of each field. So the 12-bit page offset coming from the virtual address is then combined with the 52-bit, let's say, frame number. And combined mean actually it is concatenated. So like the least significant 12 bits are the same as in the virtual address, but the highest 52-bit are different and they are provided by the page table. And then you have the physical address, which actually points to a location in the physical memory, physical location. Okay. So the frame number, this 52-bit number gives us the frame number. And then these 12 bits, they tell us, because this frame is 4 kilobyte. So it means there are 4 kilo locations, 4 kilo number of bytes. So which byte within this page you want to access, that is determined by the house. Okay, so you have this 4 kilobyte frame. Now, we were talking about the victim process, right? Now, let's say that this 4 kilobyte frame in this example or in this paper, this 4 kilobyte frame actually it contains a page from the RSA encryption decryption library. Okay. And within that page, we have some code. So it is code page, like it's not data, it's code. And it has this, it is 4 kilobyte page. It has RSA encryption decryption library. And the following is the code for optimized decryption. So as defined in the given in the paper for optimized decryption, what they do is that the message they receive they break it into, to decrypt it, they decrypt it in two stages. They first calculate MP, then they calculate MQ, and then they combine both MP and MQ to get the total message, the whole overall message. So here we are only talking about how they are getting MP. So to calculate this, they have to like calculate C raised to power DP, which will take significant amount of time, as I explained last time. If you have questions, stop me. I know I'm going too fast, and from the previous evaluation of the previous course, there was complaint that I'm going too fast, but then I can't do anything. I have to cover the material as well. Okay. So if you want to stop, please stop me. Okay. So if you calculate C raised to power DP, so this is exponent, it will take significant amount of time. So to optimize it, they use an algorithm which is named as exponentiation square and multiply algorithm. This is the kind of pseudocode for that. So this algorithm is actually, I have written it only based on the figure 2 in the paper. So in the input, it gets B, E, and M. And then it performs what it does is that it looks for, initially sets X equal to 1, and then looks for the, starts a loop from most significant bit of E to the least significant bit. I should have written here most significant bit of E down to the least significant bit of E. But anyway. And then what it does is that first it performs the scale, which is like multiplying the value of X, whatever it is. Then take the modulo, which is like scale mod M, this one. And then if you check the value of E for this at this index I, if that is not 0, then you multiply the modulo with B, this one input, and then you take the modulo operation about the result. So whatever you have here, the result of multiplication, you take mod M on that and save it in the modulo. And there is a small mistake here. Scale should be again equal to, scale should be equal to modulo cross modulo, because, and here I can set mod equal to 1. Okay, just to make, I just realized that I made this mistake there. And everyone is with me on this here. So this is how they have like, they have shown in the figure that this is the algorithm. Okay, and I just like pseudocoded it. Okay, so this is the function in the encryption decryption library, right? And that library is located at the physical frame, at this particular physical frame. So then maybe there are some things, but this is a part of the function, or part of the library. Okay, and then just to let you know that in the paper they are using this equation, MB is equal to C raised to DP mod P. So how it relates? So C becomes B, exponent DP, which is exponent, becomes E, is copied into E, and P is copied into M. Okay, but this is the component of this particular frame which contains only the code. Okay, and the actual values, when the victim process is like running this algorithm, it is running this algorithm for its own input. Like this is the coded message, this is the exponent, and this is the prime number P. Okay, so, and they are, let's say they are located in a separate page, and let's name it as a data page, right? So this is how things are working. Now, let's have a look how SPI process, what role a SPI process is playing. Let's say SPI process is running on a different core, on the same processor, but in a different core. And then it also generates a 64-bit address, as was the case for the victim. Again, its virtual address will be broken into two fields, page number and the offset, page offset. And then based on the page number, you will look into the page table, but page table of the processor, every processor has its own page table. And this page table has exactly the same frame number. Why? Because both of them are sharing the library, right? So it also points exactly to the same frame number, this one. And then whatever you get from that will be combined with the page offset. And it then will point to the same frame number, which basically means that same library is also mapped into the address space of the SPI process. Okay. Now, it's mean that SPI process and the victim both have access to this code, scale, all of this code, okay? So now, let's say that what the spy does is that it accesses these variables, scale, modulo, and multiply. So when it accesses, definitely depending upon the address, it will be mapped into the last level cache. Now, I will try to come back to later if time permits, but there are two ways how you can perform the searching, because there are multiple cache lines in a cache, right? In each set, there are multiple. First, you have to find the set, then within the set, you look for the cache line. But how the sets are searched, they are searched based on tags. And how tags are derived, from where we get the tags, we can get them either from the virtual address or we can get from the physical address. So when we use the physical addresses to prepare the tag and use those tags to look into the cache, we say that the cache is physically tagged. But when we use the tag which is derived from the virtual address and use that tag to look into to search into the cache, we name it as virtually tagged. Okay. So normally what happens is like L1, and I'm not sure about L2, but L1 is virtually tagged, but LLC is physically tagged. Why? Because of performance reasons, which I can explain later if we have time, okay? So here, now, this LLC is physically tagged, and it is like the where these scale, modulo, and multiply map in the LLC, it depends upon the physical address. And the spy process has access to their physical address, right? So it knows where they will be mapped, right? So let's say that in this example, on this illustration, scale is mapped into this particular cache line of LLC, then modulo is mapped here and multiply is mapped here, okay? Okay, and after that, let's first define some regions. So this red circle indicates that a scale operation is performed. Blue indicates that modulo is performed. This empty circle indicates that multiply operation is performed. X means that a flush operation is performed. And these two hyphens, they indicate that no data is loaded by the victim into the last level cache. Okay. So now let's see how the spy process uses the timing side channel of the cache, LLC cache, to break the RSA encryption, which basically means to find the private key of the private key for decrypting the data. So what is the private key? The private key is actually, if you remember last time we said it consisted of two parts, DP and DQ. So here the same procedure will be done, but using with the DQ. So DP and DQ, and if we can recover DP and DQ, we can recover the D as a whole. How? I will again explain. Okay, but let us first look how we can, let's say, recover the DP. And the way we recover the DP will be exactly the same to recover the DQ. Okay. So now let's say that, okay, this page is not shared with the spy. It is private to the victim. Okay. And it contains the private key component of the private key of the victim, which is, and let's say the value of this DP, this is actually an exponent, and let's say its binary representation is 101, which is 5. Okay. So now the target of the victim is to recover this one, to find that what is the value of DP. Okay, and let's see how the target of the spy is to find how value of the DP. Let's see how it does that. So let's say it's the first step, what it does is that it flushes all the 3 cache lines which are stored, to which scale, modulo, and multiply variables are mapped, these variables. Okay, it flushes all of them. And after that, let's say that it waits for the victim to execute its code. And let's say victim executes this line of code, scale. As I said, there is a mistake, but it doesn't, even if you don't do the correction, it remains the whole of the net result will remain the same. So let's say it performs the scale and it gets the data, puts some data in the variable scale, right? So after that, So that was the second, that is the second stage of the attack. And in the third stage, what it does that spy tries to read the value of the scare. Since before that victim has read the value of scare, so it loads that value into its in on L1 and L2. So it leaves behind a copy because it is an inclusive cache, right? So here a copy is left. So when victim checks and tries to read, it sees that there is a relatively lesser amount of time to read. It takes less amount of time to read the scare, okay? But when it tries to read the modulo variable and the multiply variable, since they are not loaded by the victim, they are not there, and the spy process must bring them from the memory. So it will take longer for them, right? So spy process records the time, how long it takes for reading the scale, modular, multiply variables. So let's say what we do is that the spy, the attacker, what is that? It starts building the graph. So let's say this is the threshold value. So any value, if it takes less than this amount of time, it's mean that data was in the LLC. If it takes more, it's mean data was not in the LLC. So for scale variable, it took less. Why? Because it was the copy was left behind in LLC by the victim, right? And but for when the spy process tries to access the modulo variable, it sees that the data was not there because it was flushed by itself, right? So it reads from the memory, so it takes more time. So that's why this dot is higher on the y-axis. Okay. And same goes for the multiply operation, multiply variable. So when spy again tries to read it, it's not there. It goes down to the memory, read it. It takes more time, so it is higher. I intentionally didn't overlap them to not confuse myself and you, but I guess you get the idea, right? So then after that, what happens that spy again flushes all the cache lines, which it is monitoring. Okay, flushes all of them, and then it again waits for the victim to execute. And let's say this time the execution of the victim makes progress and it executes the next line. So definitely now it will read the modulo line. And so when it will read the modulo, so it will load it here and take a copy of, okay, to its own code, which I haven't shown, but it will leave behind a copy here, right? So in the next phase, when spy tries to read the 3 cache lines, it sees that here it takes more time because data is not there, but here it finds the data and it takes less time. Here data is not there, it takes more time. So you record it in your log or whatever mechanism you have to record. So modulo takes less time and the other two takes more amount of time, more than the threshold. So you get this one, right? Then again, your spy will flush it. Again, it waits for the victim to execute. Now, note here that you are checking if E of I, and this is the first bit. We'll start from the most significant side. So the first bit is 1. So the condition is true. So control enters in the if block, right? So if it enters the if block, then what happens that it reads it performs the multiplication and puts the value in the multiplier, right? So this is what you see, right? And now this time multiply takes less time and the other two variable takes more time to read. Then again you go flush it. Again you wait for the victim. Again the victim performs the operation. This time the operation performed is modulo. So then the spy observes that okay, modulo takes less time and the other two variable took more time to be read, right? And now you are done. Now you go back at the start of the loop again and you process the next bit, which is 0 this time, right? So again, victim flushes everything. It again looks, it again first waits for the victim, sorry, not victim, spy flushes everything. Victim again waits for the victim to complete. So victim performs scare. So the data is left behind in the LLC. So now again, spy sees that, okay, for me, scare was like, it took less time for reading the scare variable, but reading the modulo and multiply took more time. Then it again flushes, again waits for the victim to execute. This time victim executes the modulo operation. And again, the your spy records the data, and so on. Now, here is the important thing, that this time we don't execute this block. Why? Because E of I is 0. So this is skipped and your control directly reaches at that, and then you go back to the for loop, right? Okay. And then again, spy flushes the caches. And again, I am not going through all the sequence, but I am directly going to the end where it has done all the things. And what happens is, like, this same pattern is repeated again here, right? Because bit is 1 again, 1, 1, right? So how now we can like recover the bits of the, how the spy can recover the bits of the private key from observing this timing. So
using the pattern?
Yeah, just look at the pattern, because if you have the pattern of this one, like scale modulo multiply modulo, it's mean that the bit was 1, right? But if there is no multiply, then it means that bit was 0, right? Because the pattern depends upon the values of the bits, right? So you can, by looking at the pattern, you can recover the bits. So 1, 0, 1, which is same as what is the private, that the key private to the victim, which we were expecting that no one can access or no one can discover, but spy was able to discover it without directly accessing it. It doesn't have the permission to access this page. Okay, so this is how they recover the one component. But this, in the same way, when your victim is executing the code for this, I haven't only put the comment here, but it will be actually the same thing. Only what will change it will be like the inputs here, right? Otherwise, everything will be remain same. So when the victim is executing this thing, what you can do is, again, you can monitor the pattern, and again, you can recover the bits for the DQ. So if you have bits for DP and DQ, then you can construct the D as a whole. How? Who has read the paper?
What was the question?
Huh?
What was the question?
I have DP and I have DQ. How can I construct the D? The DP and DQ are just components of the D. But how can I reconstruct, or how can I get the D out of them?
I wrote down that once you get DP and DQ, you can then figure out the prime numbers of N, P, and Q, which you can then use to figure out what the inverse of E is, which is the P. Because you figure out what ring the.
Yeah, mathematically they said that. I was struggling to understand what is the equation, and I also asked some other people, but I couldn't find an answer. But when you go and complete the full paper, then in the remaining section, they have this explained that if you have DP and DQ, how you can get the D. Anyone who want to answer?
So the hardness of RSA is based on the assumption that factorization of prime numbers is very hard for computers to compute. So then if you have one of the prime numbers, it's pretty easy to get the other number, since you already know the public N.
Yeah. Okay, let me answer it. Okay. So there are some algorithms which they have not included in the paper, but they have just given the references for them. So those algorithms, if you give them like 32, depending upon which algorithm you are talking about. So those algorithms need 30 to 70% of the bits of the encryption key. So if you give them like, let's say 70% of the number of 70% bits of the encryption key, it will recover the remaining 30%. So it will construct the whole RSA, whole key. Okay. But by using this approach, where you are calculating or recovering DP and DQ, they are able to recover 90% of the bits. So then on top of those 90% of the bits that they have already discovered, they can apply those other algorithms to recover the remaining 10%. And then they have the full uh, full encryption key. Yeah. So there must be a mathematical relation, but I was not able to understand it. Okay. Okay, so discussion points, I'm not going to touch them because maybe we can save them for the later part of the lecture today. So, okay, so maybe you can send me your slides. Have you sent me already? Okay, so send me slides on my email.
Question real quick, can you go back to the map?
This one?
Yeah, so on the YYY part, that is pointing to the private keys.
On the YY part, which one? This one?
No, in the page table B,
Sorry?
page table B,
Page table B. Huh.
yeah, that one that is pointing to the private keys. Was that created because of the copy on write, thing?
No. This page is not shared with anyone. This is private to the victim. So I just wanted to like highlight here that CD, DP, and P, they are not accessible to the spy. That's why I just wanted to include it in the figure. Okay. So it's not created copy on write because copy on write happens. Have you read my feedback on reading note? Yeah.
So basically
When you initially you have shared the pages, but with read-only permission. But here there is no initial page. Okay. 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 Okay, come. So you have 15 minutes, okay? So try to like keep yourself within that.
Cool. Good afternoon, everyone. I'm Joseph, and today I'll be talking about the flush and reload attack, which is a side channel cache attack. And this is from the USENIX Association 23rd Security Synopsium. Before I talk about the actual attack, I'd like to go over some background that's important to know. So what is page sharing? So page sharing is when two processes share the same memory lines. They share the same physical memory pages, and they use this for efficiency and computers. So they could save memory space, so it's more efficient. But of course, since we went over this paper today already and Tuesday, I will say the best countermeasure against this attack is quite literally just disabling page sharing in the CPU. Because you might as well stop the problem where it first occurs, because page sharing is enabling this side channel. And through page sharing, the attacker can monitor if and how the victim accesses memory locations. So what is the importance of caches in modern CPUs? So there are three levels of caches. There's an L1, L2, and L3 cache designed for speed and low latency memory for the CPU. So it's basically RAM for the CPU or just memory for the CPU, but it's way faster. The CPU can access it way faster. So whenever they use the same instructions over and over again, it's best to just keep it in the cache. And yeah, it's to maximize efficiency. Specifically the L1 cache is split into separate instruction and data caches. And it's doing this because this follows Harvard architecture. And it enables the processor to access both caches simultaneously while avoiding cache contention. So if they're trying, if the CPU is trying to fetch an instruction or is trying to get data, then they don't want to overwrite data with instructions or overwrite the instructions with data. So it also helps with contention. And this attack specifically targets the last level cache, or the LLC, which is the third level in this specific CPU. And the LLC is shared across multiple CPU cores, so the attacker can access the memory that the victim uses from a different CPU core. So specifically, the LLC is targeted here because it's also a cross-core. This cache is cross-core, so any core can access that cache, unlike the level 1 and 2, like L1 and L2 cache. And yeah, it's just not partitioned like the L1 or L2 cache, and L1 or that's what I just said, L1 or L2 caches can be partitioned to per core for a specific core. So not all processes will have access to L1 or L2 at the same time. And the LLC also has,
Correction. It's not that not all processes will have, it's not have access to L1 and L2. The thing is like this, if two processes are running on the same code, keep that figure in mind. So if they are running on the same code, then they can have access to the same L1 and L2. Like running on the same code at different times, like you are interleaving them. Process A, then process B, then process A, then again process B. So they will access the same L1 and L2. But if you restrict them, if you like pin them and you say, no, process A can run on only on code 1 and process 2 can run, process B can run only on code 2, then process A cannot access the L1 and L2 of the code 2. So they will have their own separate. Does it make sense?
a little bit, I should have had an illustration for this specifically. But the LLC also has longer persistence compared to the L1 or L2 caches. And it's because it has more memory space compared to those other two caches. So the LLC won't have its data overwritten as quickly as the L1 and L2 caches. So it makes more sense to attacker to focus on the LLC.
And sorry for interrupting, but I just want to correct that don't use the word partitioning, because partitioning basically it is a technical word and it means partitioning a cache means you physically you have same cache, but you logically partition it among multiple processes. I think here what you are want to say is that LLC is not private, it is shared, right? So physically it is same, but it is shared, right? It is not partition. When you say partition, it means that I give you logical sectors in the LLC and then I assign each sector to different process. At each. So
Oh yeah,
when I wanted to like.
when I wrote,
Someone will read, someone will read this line, they will, and they know what is the cache partitioning is, they will misinterpret.
yeah, when I wrote that, I meant like some processes will mainly only use like the L1 cache instead of L2, and then some will just use L2 instead of L1, and they won't they'll just be partitioned specifically for that core, not really I don't know.
The right word to say is private. L1 is private, L2 is private, LLC is shared.
Okay, got it. But yeah, and since the LLC also has more memory space, and it's the lowest level of to the CPU, its access time is slower, so the attacker can use that to their advantage to differentiate whether a memory line was accessed or not by the victim. So let's dive right into the attack. So what is the flush and reload attack? So this is a cache side channel attack that targets the shared memory pages that are stored in the CPU cache, specifically the L3 cache or the LLC. And it's first done by establishing these shared memory pages, and these memory pages must be an inclusive cache, meaning that all the data stored in L1 and L2 will also be copied to L3. So this attack specifically targets the L3 cache. The attacker can then flush the memory location with the CL flush instruction provided by the x86 CPU architecture. Another way to prevent this attack is to just limit permissions from how the computer can use the CL flush instruction. Because the computer can just use that instruction willy-nilly. But flushing the memory forces the victim to reload the data from main memory into the cache if they access it. And by measuring the time it takes to reload, that same memory line will tell the attacker if the victim has accessed it. Then the attacker would wait for the victim to access the shared memory page, which whenever they access that memory page, like Professor Mustafa talked about, when they access that memory page, they could be doing RSA decryption operations, or you can even log user keystrokes with it, or any other process that's using that memory line. So when the attacker reloads the flushed memory location and measures the access time, it will tell them that if the victim has accessed it, and if the access is fast, then the victim accessed that memory page due to the data being brought back into the cache. And if the access is slow, then the victim most likely did not use that memory page. But this isn't 100% guaranteed all the time, because sometimes that memory will be like accessed at the same time whenever the attacker reloads the data. So this is at least 90% successful. And an example of this attack is when an attacker monitors specific memory locations that are accessed for each bit of a private key. And you can infer the key values after repeatedly observing those memory locations that do like either the multiply or modulo operations for that algorithm. So why is this important? I have a funny illustration here on why this is important. So this attack can be used to steal cryptographic keys, which are used everywhere to keep everything private and secure. If the attacker can figure out where an RSA algorithm stores its secret keys, then they can monitor the cache accesses to reconstruct the data. The attacker could also spy on keystroke timing, GUI operations, or other authentication operations. Plus, this is also not just limited onto a single computer, but this attack is more significant because it can be exploited within cloud computing. The attack extends to virtual machines because they also use features to share memory within the CPU. One of the features that they specifically say that they use is like deduplication with virtual machines and their memory. So here are some strengths and weaknesses of the attack. So this attack is a high resolution and low noise attack. The way data extraction is conducted through the LLC makes this attack a very high resolution attack with high success rates. And it pinpoints exact memory location accesses made by the victim. And the attack extracts 98.7% of the bits on average on the same OS and the same OS scenario that they went over in the paper. And worst cases come out with 95% through 90% of bits extracted. And the attack is also able to focus on functions such as key-dependent operations for cryptography. This attack is low noise because it doesn't always rely on guessing which cache sets are being used, such as demonstrated in the prime plus probe attack. So in this specific attack, there's isolation from unrelated processes that won't affect it, and it enables more reliable and or more repeatable attack process. And two weaknesses of this paper is that the attack relies on one main feature of the cache system, which is page sharing, and that it has to be the specific CPU. It is inclusive and it does page sharing. And this attack mainly focuses on a specific Intel x86 architecture. And so a good question is this attack also possible on ARM systems that use Ryzen or AMD CPUs?
Okay, anyone who wants to answer this? Does this attack be possible on ARM system?
You.
Yeah, the paper does state that the attack is not possible on the newer AMD processors. It is however possible on the older generation AMD processors. And that is one of the questions I had was, why is that possible if the older AMDs share some sort of characteristic with the new x86 architecture? I was thinking maybe it had to do with the policies for caching. I think they both have similar, it's called inclusive caching, where they share their caches amongst the hierarchy.
So, but R is different from AMD, right?
Are they the same? I think they're, oh,
So the paper says that the ARM architecture has these instructions to fix the cache lines, but these instructions need elevated privileges. So then
Are you talking about ARM or AMD?
ARM. Yeah, we need the process that wants to fix the cache lines needs elevated privileges. So then a process can't epic remember lines from the.
So how it makes the attack fail? How it makes the attack to fail?
Elevated privileges.
Because
Because it doesn't allow to use
yeah,
instructions.
spy is a user level process and it cannot execute CL flush.
With the AMD processors, their failure was they just don't have the CL flush instruction.
Okay. So
So
they don't
they
have
just don't have the ability, period. And they don't have the inclusive caches.
So which is
like,
also
things that
required.
x86 does.
yeah. Now we can talk about countermeasures. As previously stated, the first and most obvious countermeasure would just to completely disable page sharing within the caches, which will prevent processes from sharing memory to get rid of the issue where it began in the first place. So you could also limit the power of the CO flush instruction or just add permission checks to using it. And
So for the first countermeasure, what will be the counter argument? Like, what's the disadvantage of disabling the memory sharing of page sharing?
it makes the CPU a lot more efficient when you use page sharing, but it's a trade-off of having that vulnerability.
Yeah, so
Being more reliable in the operation system, that'll cause a lot more issues in the memory.
now you will need, if you are not sharing memory, one thing is like, you will require more memory to service two different processes which were previously sharing the same pages, one thing. Second, it can also not only increase the memory requirement, it can also reduce the performance, because previously what you, like, let's say you are a processor. So if you were accessing the page A and then process B is running, you already had that page in the cache. But now you have not shared, so for process B, you need to go down to memory and bring its own page, which may contain the same data, but still you need to go down to the memory, which will waste the time.
Yep. And in cloud computing or for virtual machines, you can switch off memory deduplication, which is basically the same thing. The memory saved by sharing pages in a virtualized environment does not justify the breach in like isolation between guests. And here are my references. It's just the paper.
Thank you. So, do you have discussion points or questions or comments or other than you ask something, giving a presentation?
I thought this paper was really in-depth, and I wanted to add more illustration on how to actually conduct like the RSA attack, or how, like basically what you did in your slides is how to actually extract data and how all the timing works and stuff.
Yeah, but they cannot include that in the paper because, yeah, they maybe they have, I don't know, in the paper was presented in 2014, I guess, right? So maybe when they presented in the conference, they had a discussion there, but we cannot put those kind of things in. Okay. So, okay, so.
Or I got one I can maybe lead you into.
Mm.
And I don't know, I mean, I know you're not familiar with hardware stuff, but with this, so in 2014, they had these CPUs and these were already on the market being used. would they be able just to send out firmware update and say, okay, everyone update, and this solves the issue with Intel, or would they have to replace all of the CPUs? And everyone would have to buy a new one?
That's something that I also looked into because all of the mitigation strategies that they suggested were all software-based, which doesn't really attack the problem at hand, which is a side channel attack that's attacking the hardware directly. Which I think a better strategy to mitigate this issue would be directly addressing the hardware rather than the software mitigation.
Yeah, but as they mentioned in the paper, yeah, I mean, processors are already in the market, people have deployed them in their products, they are on like the running systems. You cannot like, ask them to give them back, right? So that's why yeah, maybe that is like, from the perspective of protection, that is the best maybe approach, but from the perspective of the cost and feasibility, it is not. So the software-based solution is better, but then software-based solution has the limitations, like for example, as if I don't allow the page sharing, but then it will blow up your memory. And for example, deduplication. So deduplication will also result in the same thing. If you don't allow the deduplication again, you will be having more memory requirement. In the paper, they have mentioned, they informed what I don't know the company which was making this GNU PG library or software which had this vulnerability which they exploited, and they fixed their code, right? But
Yeah, I wanted to add on to that too. I remember in the paper it said that GPG made, they released a new version. After, I guess they talked about it with the GPG team, and they made, that new version just fixes the issue. It's, I guess even if you still had that same vulnerable, like CPU running like on that same scenario, but if you had the new version of the GPG, like encryption stuff, I guess it wouldn't, be vulnerable, like, would be safe. It uses some different multiplication thing to
The
prevent
algorithm
this.
is distinctive of its runtimes, that doesn't distinguish the operation.
Oh, yeah.
so I think there are two aspects to that. Yes, they have released a new version which fixes that problem, but it potentially creates another problem, which they have mentioned in the paper, that theoretically, if you remember, and if you remember it, they have a new version, an if statement, right? If this is equal to then set this equal to this. So there is a conditional execution, right? So if there is conditional execution, maybe not this attack, but some other side channel attack can be used to, side channel can be used to launch an attack on this new software, okay? Which they have also mentioned, right?
Branch-based?
Something like that, branch analysis.
Yeah, branch-based analysis
Yeah.
on how the compiler
Yeah.
executes the.
That's thing, and second, that yes, they discovered the problem with the software, which they then combined with the side channel to recover the private key. But that problem which they have discovered is discovered only in one particular software. Maybe the similar or same problems exist in other, similar, where you can actually, just by looking at the pattern, timing patterns, you can extract the bits. So, and maybe the same approach you can use not only to break RSA, but some other encryption algorithms as well. I don't know. Right? Because if it is still, if the approach is applicable, where you can see that, okay, the timing pattern depends upon the input values of the secret key, private key, then you can extract it. Right? Okay. Any other question, comment you want to make?
Yeah, this might be nitpicky, but on the threshold, the paper mentioned the way they chose the threshold, they would look at how long it would take to access memory for L3 cache, and then they had the offset for how long it takes for L2 and L1, with a little bit more offset to make that threshold. I was wondering what would happen if you made the threshold closer to what accessing main memory would look like. Like, wouldn't you have more leeway for detecting if there's an overlap between the victim and the next flush reload happens? if that makes sense. Cause that was one of the issues where it wasn't catching if they overlapped. So we made that threshold closer to what main memory accesses rather than closer to what the cache timing was.
Yeah, I am not sure if I 100% understood your question, but I see what you are explaining, like the more accurately you correct, actually the problem is that sometimes the excesses are made by the victim, but spy is not able to detect them. And that basically because of the threshold value they have set. So maybe yes, by changing the threshold, they can improve the accuracy of their detection of the bits. Yeah, it is possible. Okay, so what are the limitations? Anyone who want to point the limitations of the? Okay, go ahead.
So this whole thing was in control lab environment, which didn't have much background processes running. So in a real world scenario, I don't think there will be much more noise,
Yes.
and there will be false positives and more error rate, I'll say.
Yeah, so when they were running the experiment, what they did that on the machine, they were running only two processes. One victim and one is spy. So as a result, what happens that, and even when they were running only two systems, if you look at figure 6, they have this green part where they say that these cycles were missed or these slots were missed by the spy. And why? Because maybe the spy process was not even scheduled by the operating system in that slot. So if it is not scheduled, it cannot execute, and as a result, it cannot be at the timing, right? But at the same time, maybe the victim was running on the different code, right? And this is when they are running only two operating system and two user level processes. Now, if you have lot of other number of processes, and number of processes are more than the number of cores, then definitely spy will get kicked out, right? It cannot occupy all the time. And as a result, the accuracy of it, how accurately it can time the victim accesses will reduce. Any other limitation?
I think the paper discusses that there's like 4 factors that the flush and reload technique relies on. One is being like the GPG, where you know what the code and the access pattern looks like in cache. The other being memory sharing, which Joseph mentioned earlier in his presentation. The accuracy of the timing between like when they're accessing cache, and the last one is like the unlimited quotations, unlimited power of CL flush, just like the power it has.
Yeah, so
any of these being blocked means it doesn't work.
yeah. And one limitation they have, they have mentioned in the paper is this, like, here they have only one victim running, right? Now, if you have multiple other processes, you have one spy, let's say I'm spy and all of your other user level processes. And we are sharing the library, keep that with the animation in the mind. So all of us are sharing the same thing, and I am the spy. I cannot see that who is loading the data into these LLCs, like which of you is. So I cannot make any information out of it. I will get the pattern, but it will be a noisy pattern without any information. Yeah. Okay.
To add on that real fast, it would just basically mean like if you have a virtual machine, if you have a virtual machine with a bunch of different, or we have a VPS, the VPS has, 10 hosts on that machine. We're not gonna be able to identify which individual VM is running on that machine.
I didn't get your question, say it.
So we wouldn't be able, so they talk about the virtual machine side a lot, right? So we have about having a hypervisor and then a bunch of VMs. We wouldn't be able to identify which VMs information is coming from.
Yes.
Okay.
Yeah, same for it applies to both, like if you have multiple VMs and like one of them is spy and other are like one victim is like your targeted victim is one of the remaining VMs, but all the VMs are running the same function, you don't know who is filling the cache. And same is true when you don't have cross VM attack, but you have cross-process attack on the same OS. You have multiple processes, the same thing again is valid. Same limitation again applies. Okay, then, yeah.
The question from last class was, a split, section of data and execution, for cache in the L1 level. What was the reason?
Why they are,
Yeah.
why L1 is separated into separate instruction and data cache? Yeah, okay, I will explain, and I also have another question related to it.
Yeah, that one specific
Okay,
is
so
specifically called.
before I go there, I have some general feedback for you. For everyone actually. So when you're preparing slides, use the slides only to guide your presentation, like put the bullet points, not like paragraphs. Okay. And put more figures if you can. Put figures, illustration in the slide. And also try not to include in the discussion day slides, try not to include what is already covered in the background. Okay. I'm not like saying no, you did it, but I'm just giving a guideline for everyone. Yeah, okay, thank you. So, yeah. Okay, before I answer that question about caches, separate caches, how many of you would have taken this course if it was not required for you? After like seeing what you have seen in 3 weeks? And like exclude me from like maybe I'm like bad teacher, but after reading the papers, how many of you like have developed some kind of interest?
They're all like this.
Yeah.
Okay,
That's the best one.
okay, yeah, because it was like more specifically targeting a particular approach.
It was much more.
Yeah,
approachable
yeah.
than the other.
Because other were more general. The first one was like survey, second one was a like general approach instead of a particular attack. Okay, so coming back to your question, we have time. So the question he asked is like L1, it is actually splitted into separate instruction cache and data cache. But L2 is not, L3 is not. Why L1 is separated into instruction cache and data cache? So which, if they are not separated, it means they contain both instructions and data, because everything is coming from memory, right? And then from here, the instructions go here and data go here, right? So remember the pipeline: fetch stage, decode stage, issue stage, execute stage, execute our memory access, and write back stage, right? So what happens in fetch stage? You fetch the instruction to execute, right? From where do you fetch? From memory, right? And in execute or memory stage, what you do? And here either you are executing if it is a, let's say, logical instruction, but if it is a memory access instruction, you are either reading from the memory, data from the memory, or writing data into the memory, right? Okay. So here you need to access memory for getting instruction. And here you need to access memory for reading or writing data, read-write data, right? Now, let's say instruction X is in this stage, instruction Y is in this stage. You are clear on this, like different instructions will be in the different stages at the same time, right? So let's say at a particular clock cycle, instruction X is occupying this stage and instruction Y is occupying that stage, right? Now, if we have single memory, L1 is, and remember, pipeline always reads from the L1. It cannot read directly from L2. It's not possible. Okay. So if we have one L1 and it contains both instruction and data, so it wants to read from here the instruction. And at the same time, this wants to read instruction from data from here, from this one, right? So then, and if we have fixed number of only, if we have only one read port, we can only read one entity at a time, let's say. Then it will, we can read one cache line, we can perform one read operation, then one of them has to wait, right? So then either we have to block the fetch operation or we have to write the memory access operation, right? So that's why what they do is, and anyway, whatever the fetch needs, fetch stage needs, the instruction, the fetch stage need, it is instruction. And the instruction in the memory stage want to get access the data, not instruction. So their needs, their requirements are different. So that's why they say, okay, just split it. And this can give instruction here, and this can give data here. What is another option? So you get it now, the question, why we split it. So now, if we split it now, none of them need to block. What is another option instead of splitting?
Will be in different cache levels? If you access,
We already have cache levels.
I mean, like, instead of grabbing the instruction and the data from the same cache level, you grab one from one cache level and you retrieve the other one from.
But then the other one which you retrieve, let's say from the lower cache, it will be slow, right? Let's say if you're accessing data from here and instruction from L1, so you are fetching instructions at a higher speed and you are reading data at a lower speed. So it will overall slow down. There is no advantage of reading the instructions at a higher speed because they are slowed down in this stage by lower access to the, let's say L2. Slower access to the L2. The other option is like, you can have two reports. One gives you instruction, other gives you data, right? But then everything is inside it, and then you need to do searching, and you need internal mechanism to find out a track where the instructions are stored and where the data is stored. And all the time, either you have to, it will take time to do the searching, or you have to like all the time track it where they are, or develop a mechanism where data always go to one section and instruction always goes to the other section, which is actually the same. Okay, so instead of searching different type of data, if you have like, you have one jar and it contains red balls and green balls. So if you want to search like, and we don't know if they are in equal number, maybe there are much more number of green balls than the red balls. And you want to search the red ball, it will take more time. But if you have two jars and one always contains only red balls and the other always contains green balls, it's easy. Okay, so the submission is open. You want me to stop, or I just want you to discuss another thing? Okay. So remember I said that this one, L3 is physically tagged and L1 is virtually tagged. But why? Why L1 is virtually tagged, why it is not physically tagged, and why this one is not virtually tagged? Because the addresses generated by the core, they are virtual, right? Virtual addresses. Now, if I use the physical address to tag the instruction cache or L1 cache, I need to first translate it, right? And if I translate it, it takes time. And L1 is the most frequently accessed cache, right? So since it is most frequently accessed, most frequently I will like, again and again, I will need to do the translation, which will slow down my execution. So that's why this is like the prime reason that we use the virtual addressing to address or index the L1. However, here we use the physical, because if we don't use the physical address and we use the virtual address, then we cannot share the data in LLC among multiple processes, just like we saw in the example.
because virtual addresses are different. For virtual address for two processes are different. So if there are two are different, one will be pointing at one location, another will be pointing at another location. Even when they have the same data, there will be no sharing. So there will be like duplication or wastage of memory. I don't know whether it makes sense or not, but I just wanted to like give the reason why we use virtual tagging for L1 and physical for LLC. Okay, everyone done with the submission?